Welcome to our lesson on dilations. For this section, you will need a ruler for one of the examples. If you don't have one handy, don't give up. Still watch the video. You'll get plenty out of it still, and you can do the example where you need a ruler at a later time. What is a dilation? Well, a dilation is actually another kind of transformation. You probably remember talking about transformations a couple of units ago. But the difference between the type of transformation that a dilation is and the type of transformations that we talked about 2 units ago is that the pre-image in a dilation will not end up the same size as its image. Therefore, dilations are not isometric transformations. The image will either be larger or smaller than the pre-image. The way a dilation works, it does involve a point, much like a rotation does, but other than that, they don't have a lot in common. The point we call the center point of the dilation. From that center point will come rays. The ray will go from the center point to a point on the pre-image. I am going to highlight the 3 vertices on this triangle. Even though there are infinite points on the triangle, I'm going to highlight these 3 key vertices. To get the image, in this case, if you move from the center point to the pre-image and then even further away from the center point, you would get an image that is larger than the original pre-image. So A prime, B prime, C prime is proportionally larger than ABC. If that's the case, they call this, shockingly, an enlargement. Now, if you move from the pre-image closer to the center point along these lines that we've drawn, the image would actually get smaller than the original pre-image. A double prime, B double prime, C double prime is a cute little chip off the block of ABC. When the image gets smaller than the original, we call that a reduction. So while the pre-image is not congruent with the image, there's still a relationship between the two. Distances between the pre-image and the image are proportional. We have what's called a scale factor in these dilations. The scale factor describes what you have to multiply this distance by in order to get this full distance. If you're multiplying by a positive number greater than 1, you will go beyond A and get an enlargement. But if you multiply the distance by a fraction less than 1, you will not make it to A, and you will get a reduction. So an enlargement has a positive scale factor greater than 1, and a reduction has a positive scale factor less than 1. You know, like a fraction, 1/2, 2/3, 4/7. Multiplying a number by one of those will make the number smaller. Let's get the definition of a dilation. A dilation with center point C. We've got the blue center point plotted here. I'm just going to label it as C. There's my center point C. And scale factor K. We'll talk more about that in just a minute here once we get some more things labeled. Is a function that maps the pre-image point P in a figure. So now we've defined a point on the pre-image called P. That's what this definition is talking about. So that P prime is on ray CP. Well, ray CP is this thing. P prime is, keep following that path, that's what they're saying, is going to be on that same path. So I'm going to label this point P prime. And so that CP prime, so now they're talking about the entire distance from here to here, is just going to be some number times the shorter distance from here to here. That number that the short distance gets multiplied by to form the long distance is our scale factor. K can't be 1 because that wouldn't change the pre-image. If this distance were multiplied by 1, it would be the same distance and nothing would change. It wouldn't really be a transformation. it should be noted that if point P were on point C, then P prime would also be on point C. Therefore, P and P prime would be the same. So if P were also right here, the distance from C to P would be 0. Therefore, the distance from P to P prime would also be 0, and all 3 points would be one and the same. Let's look at an example. We want to create triangle A prime, B prime, C prime based on the pre-image triangle ABC. The way we're going to do it, we're going to have to measure. We're going to use a dilation with a center point of A. So A is also part of the pre-image. So this kind of goes back to if a point on the pre-image is on the center point, then A prime we'd also expect to be on A as well. I'm just going to go ahead and write that down while I'm thinking about it. So now we still need to find B prime and C prime using a scale factor of 3/4. So I don't know how long this segment AB comes out on your paper, but you'd want to measure it with a ruler. When I measure it with my ruler, I get 1 foot, 12 inches. Obviously, it'll be less than that on your paper. Now the problem is, I need 3/4 of that because that's my scale factor. Well, 3/4 of 12 is 9. So I'm going to measure 9 inches down the side AB, and that's going to form my B prime. So I've got A prime, I've got B prime, I just need to get C prime. To find that, I can measure side AC with a ruler. I'm getting about 28 inches. If I take 3/4 of 28, I get 21. So what I'm going to do is I'm going to measure 21 inches from A toward B, and that's going to be my point C prime. Since it's a triangle, there's obviously infinite points on this triangle, but those 3 vertices represent them very well. So what I'm going to do then is draw in the rest, and you get the transformed triangle. A prime, B prime, C prime. Here's another example. This is an enlargement because the ellipse with points T and S on it is smaller than the T prime, S prime ellipse. All right, let's label in what we know. It says RS prime, so that is the entire horizontal distance along the bottom, is 10 units, and SS prime, sounds like a ship, that's 4 units. We want to determine the length of RS. And you can use segment addition here. If the entire distance all the way across from R to S prime is 10, and you know a piece of that is 4, then the rest must be 6. So that's a pretty quick question to answer. Determine the length of segment RS, 6 units. I don't know, they didn't give us units in the problem, so we can't give them units in the answer. Then determine the scale factor of the dilation. To calculate the scale factor here, we have to realize right off the bat, our scale factor has to be greater than 1 because this is an enlargement and not a reduction. To calculate the scale factor, you need to figure out, and we're always going to start from the center point, point R. Start from the center point for all these calculations. Going all the way out to the edge would give us the distance RS prime. We're going to make a ratio of RS prime, the long distance, over, starting again at center point R to S. That ratio will be our scale factor, which is 10 over 6, which of course will simplify to 5 over 3. So our scale factor is 5/3. 5/3 is greater than 1, which is how we got an enlargement and not a reduction. One last example. We are given a segment MN and asked to find its transformation M prime N prime based on doing a dilation with such and such a center and such a scale factor. All right. If they ever give you a coordinate plane dilation, if they're really, really, really nice to you, and usually, surprisingly, they are, they'll make the center of it at the origin, like they are here. The origin is the point 0, 0, of course. Because for a dilation with a center at 0, 0 and a given scale factor, they're going to call that scale factor k. In our case, it's 2.5. For whatever pre-image points you want to run through this command, this function, you simply have to multiply its coordinates by the scale factor x. So if you start out with xy, like we are here, m has the coordinates 0, 2 on its endpoint. M prime is going to be the scale factor 2.5 times the x value, and the scale factor 2.5 times the y value, which will equal 0, 5. That is right here. We'll have m prime. For n, whose coordinates are -3, -1, n prime will have 2.5 times -3, comma, 2.5 times -1, which is just -7.5, -2.5. Don't get too worried about the halves on the coordinate plane. Just because they're not tick marks there doesn't mean they don't exist. So -7.5 means 7 full units and half another. And then we got to go down 2.5, so that's down 2 units and then half another. You end up in the middle of a box. That's okay. It's still n prime. And then you can draw a segment connecting the two, and you've transformed the whole thing. So another way of wording this is you can simply multiply each coordinate of the pre-image by that scale factor in order to get the transformed coordinates. So just to review, dilations are not isometric. They are transformations, but they're not isometric. They can make the pre-image get bigger, called an enlargement, if you multiply by a number greater than 1. They can make the pre-image get smaller, called a reduction, if you multiply by something, a fraction less than 1. And while the pre-image and the image won't be congruent, their side lengths will be proportional because of that scale factor. One last question for you to ponder before we say bye-bye. What would happen if we had a negative scale factor? Something to ponder. It might come up. See what kind of answers you can come up with, as we'll be doing some problems using this in the very near future.